For the final part of this course, we'll introduce the Graphics Processing Unit, or GPU. GPUs are specialized hardware that were originally developed to render real-time graphics, but they've now become widely used for a large range of computational tasks, especially those that focus on high data parallelism. For the right kinds of problems, GPUs can deliver performance gains over similarly priced CPUs of up to several orders of magnitude. This is thanks to their fundamentally different hardware architecture that's primarily designed for high throughput and parallel execution. For example, in large language model inference, my GPU delivers performance gains of 40 times over my CPU, despite both of these devices being similarly priced. In the first part of this video, we'll start by examining how GPUs differ from CPUs, primarily by focusing on their architecture and execution model. In the second part of this video, we'll focus on how we can leverage the high parallelism of the GPU by using an array-based programming model. We'll explore how we can easily write concise, expressive code that can run on both the GPU and the CPU. And of course, we'll be doing all of this using the Julia programming language. By the end of this video, you'll have a better idea of the strengths and weaknesses of the GPU, and you'll have some idea of how you can write GPU-accelerated code using array abstractions. Let's get started. What you're seeing here is a simplified diagram based on the architecture of an NVIDIA A100, a GPU that's commonly found in high-performance computing clusters. Unlike CPUs, which rely on a separate system RAM, GPUs typically include their own dedicated onboard memory, located physically close to the processing units to minimize latency. The A100, for instance, uses a type of memory called HBM2, high bandwidth memory, which is particularly well suited for parallel workloads due to its exceptionally high memory throughput. Before any computation can begin on the GPU, the required data must reside in its device's memory. Typically, this involves copying the data from the main system's RAM via the CPU over to the GPU, usually across a PCI Express connection. In systems with multiple GPUs, data can be transferred directly between them using high-speed interconnects. In the case of NVIDIA GPUs, this interconnect is called NVLink. Just like CPUs, GPUs employ multiple levels of on-chip cache to reduce latency and maximize memory throughput, ensuring that the many processing cores are not idling while waiting on memory accesses. So far, the GPU might appear architecturally similar to a CPU, but we need to zoom in to one of the processing areas to observe the main difference between a CPU and a GPU. Most GPUs consist of many individual processing clusters. Each manufacturer uses different terminology, but in the case of NVIDIA, the streaming multiprocessor, or SM, is one of the fundamental execution units in the GPU. Each SM is similar to a multi-core CPU in and of itself, but it follows a single instruction multiple thread, or SIMT, parallelism model, which means that each thread must execute the same instruction in parallel, whereas a multi-core CPU is far more generic and each thread can execute completely independently. Within each SM, we find smaller execution blocks that share access to a localized L1 cache. So let's focus in on one of these smaller blocks. The actual execution is carried out by specialized hardware units. For example, in NVIDIA's GPUs, these are known as CUDA cores. These cores are far slower and less complex than typical CPU cores and are only designed to perform simple mathematical operations in parallel. Each CUDA core has a limited set of operations that it can perform, usually 32-bit integer or floating point arithmetic. High-end GPUs also support 64-bit floating point or FP64 operations. However, these cores are typically much fewer in number. For example, in this data center class GPU, there are half as many FP64 units as FP32 units. Whereas a consumer-grade GPU, like my 4070, has just one FP64 unit for every 64 FP32 units. This disparity is why GPUs are generally used for applications which can tolerate lower numerical precision, like graphics rendering or deep learning, where the overall throughput matters much more than per operation accuracy. As GPUs were first designed for graphical operations which rely on trigonometric functions like sine or cosine, each block will have a special function unit, or SFU, which provides hardware-backed support for efficiently computing some mathematical functions. Another key component in modern GPUs is the tensor core. These are specialized units designed to accelerate matrix operations, a critical bottleneck for deep neural networks and many other scientific computing workloads. For all of these many cores to operate effectively, they need to be continuously supplied with data, and not be waiting to send off results to onboard memory. That's the job of various I/O units responsible for load and store operations between the onboard memory and the processing cores. Execution instructions are managed and scheduled by dedicated hardware, and temporary results required mid-computation are stored in fast access memory called the register file. Within each SM, there's also a region of cache memory shared across all the cores in a block. Shared memory acts as a user-managed cache, allowing threads to communicate and share intermediate data efficiently. It's the programmer's responsibility to decide on how to use this memory and guard against any race conditions that might come up by correctly using synchronization primitives. Zooming back out, you can appreciate the scale of parallelism on a GPU like the A100. This is just a simplified diagram with fewer regions than an actual A100, but the real device contains 6,912 FP32 cores and 3,456 FP64 cores, and this isn't even including the Int32 or Tensor cores. In terms of raw compute, the A100 has a theoretical peak performance of 20 teraflops of FP32 performance, and that jumps to around 150 teraflops when you're using Tensor cores. Teraflop is just a measure of throughput and stands for 1 trillion operations per second. For a little bit of context, the A100's theoretical max performance is roughly equivalent to the floating point performance of a top-tier supercomputer from just over a decade ago. In fact, back in 2012, a single A100 card would have ranked around 250 on the top 500 list of the world's fastest supercomputers. Now that we have a better understanding of what GPUs are and what they're capable of, the next question is, how do we actually run code on them? Since programming GPUs can be quite complex, several software platforms have been developed to simplify the process. These platforms often provide both implementations of commonly used algorithms and a domain-specific language tailored to GPU programming. The most widely used of these is CUDA, a proprietary framework developed by NVIDIA. CUDA allows developers to write programs that execute on NVIDIA GPUs, usually written in a restricted version of C with additional GPU-specific syntax and semantics. However, because CUDA is proprietary, it only runs on NVIDIA hardware, which introduces a degree of vendor lock-in. There are alternative platforms, although they currently have smaller ecosystems. For instance, ROCm is AMD's answer to CUDA, and OneAPI is Intel's cross-platform framework. These frameworks are promising, but generally less mature than CUDA. If you're using an Apple device, you likely want to explore Metal, which is Apple's graphics and compute API. There are also some vendor-agnostic solutions like OpenCL, which aim for broad compatibility across a range of hardware. In the next part of this video, we'll dive into how to actually run code on the GPU. I've outlined these platforms so you're aware of the options available depending on the hardware that you have. Since this is a Julia course, we'll be using packages from the JuliaGPU ecosystem. For the later demo, I'll be working with CUDA.jl since I've got an NVIDIA GPU. But if you have a different GPU, you should be able to follow along using one of the sister packages to CUDA.jl. For AMD GPUs, this is AMD-GPU.jl. For Intel, this is OneAPI.jl. And finally, for Apple, you should look into using Metal.jl. The syntax for each of these packages is roughly the same, and you should only need to make a few minor tweaks to be able to follow along with the rest of this video. So now you know which packages are available. What do these packages actually provide? Well, primarily they serve as an interface to the underlying GPU libraries. For example, CUDA.jl gives you access to the CUDA-C library from within Julia. This includes convenient bindings for GPU-based operations, for example, matrix multiplication, summation, reduction, fast Fourier transforms, and more, all by calling into pre-written, highly optimized CUDA libraries that are provided by NVIDIA. Today we'll be focusing on using these high-level idiomatic wrappers, which makes it easier to get started with GPU programming. These wrappers are a great stepping stone for jumping into GPU programming, and they can let you easily accelerate array-based algorithms without too many changes. What's quite unique about Julia's approach to GPU programming is that packages like CUDA.jl also provide a way to write custom GPU code in pure Julia, which can be compiled down via LLVM into code that can be run directly on the GPU. Programming code directly for the GPU has many restrictions and is a much more advanced topic that we won't cover in this video, but we'll cover in the next video. For now, let's jump into VS Code and focus on the easiest way to get started using the GPU with Julia. The code I'll be using is available online in a public GitHub repository that you can access with this link, which you can also find down in the description. Now we're in VS Code, the first thing that we need to do is install the CUDA.jl package. We can do this in an open Julia REPL by pressing the close square bracket key and typing in add CUDA. I've already done this on my machine, so I'll skip this step. Once you have CUDA installed, you can just type using CUDA, and this will precompile the CUDA package and load everything in to make sure you have everything you need to get up and running with your GPU. What's nice about CUDA.jl is that you don't need to go online and find the right CUDA toolkit to support your system. The package will find the right binaries for your system and automatically download and install these binaries for you. But otherwise, this feature makes it very quick and simple to get started with CUDA. When you've brought in CUDA, you can run CUDA.versioninfo to make sure everything is installed correctly. And this information is useful if you ever find a bug and you need to submit an issue on GitHub. At the bottom of the output, you'll also see the GPUs that you have available on your system. In this case, it's correctly detected my NVIDIA 4070 GPU. To make sure that we're able to use the GPU without any issues, you can also run the CUDA.functional function call, which in this case returns true, and so we're ready to go. The first type of operation that's very easy to parallelize on the GPU is simply a vector addition operation. The way we would do this on the CPU is to create two vectors a and b, making sure that they're the same size, and then we can simply run a dot plus b, and this will create our new output vector. Another way we can perform the same operation is by pre-allocating the memory by using the similar command, which will essentially just allocate another array that is the same type as the input array. You can then use the broadcasting notation to insert the result of a dot plus b in the pre-allocated memory C. These steps are essentially the same on the GPU, but we just need to change the type of the arrays and where the memory is stored. At the moment, the memory for A, B, and C is stored in the host system memory, which means it's stored in your main system RAM. But by default, your GPU can't access this memory, and so we need to copy it over to the GPU in order for us to run any operations there. There's a few ways you can do this with CUDA, but one way is to use the CU function, which will convert the array A into a GPU array. This will also do some extra conversions as well to make sure that you're using well-supported data types. For example, it will likely convert your floating point numbers to float 32. If you want to avoid this, you could always use the CU array constructor directly, which won't do any conversions. If we run this function, the array will then be copied over to the GPU, and the type of the array is different from the input type A. Instead of a normal vector or array type, you'll see the CU array type, and this gives information to the type system about where this GPU lives. In this case, it's living on our NVIDIA GPU. All the data that's required for a given operation should exist on the GPU before you begin any operations, and so we'll copy over both A and B. Once we have A and B available, we can run the same operation as before with the same syntax, so A dot plus B, but making sure that we're using the GPU versions of these arrays. The first time we run this operation, it might take a few seconds to run, and this is because it's compiling code to run on the GPU for the first time. Once this code is compiled, you can simply run the command again, and it will run almost instantaneously. If you need to pre-allocate any memory, you can also do this with the same similar function, and because the input type of the A GPU variable has changed, this will not just create a new array, but it will make sure this new array is created on the GPU. We can verify this by checking the type of the C GPU variable is in fact the CU array type. We can then use the same in-place broadcast notation that we did before to write the result of A dot plus B into the result of C, in this case using the GPU variables. Now, if we wanted to check that the results from the GPU and the CPU are equal, we'd want to use the isApprox function. Unfortunately, if we try to run this operation, we'll run into an error. So let's take a closer look at this error. Now, this error looks quite complicated at first because there's quite a large output, but most of this output is due to the types being printed. What we should focus in on is the type of the error being displayed. And the error that we found was a kernel error. And the reason why we got a kernel error is because we're trying to compile a new program to run on the GPU, and the programs that run on the GPU are called kernels. And that's because the isApprox function is available in the base library, and the base library doesn't know anything about GPU arrays, but it relies on functions like broadcasting, which the CUDA package defines for GPU arrays. And this broadcasting compilation usually works, but you have to respect a few rules, and one of the rules is that all of the arguments that you pass in need to be of a bits type, or just a GPU array directly. Now, you might not have heard of bits types before, but the error gives us some more information that tells us what bits types are. So it says that bits types, which are plain data types which are immutable and contain no references to other values, can be used in GPU kernels. And there's even a function in the base library to determine whether or not a type is a bits type. So if we bring up the reference for a bits type, it means that the values stored within only contain primitive values and other is bits type types. And the reason why this is important is because these types have a defined memory layout. And you can essentially treat the type as a big block of memory that can be copied around without having to worry about references to other parts of memory. So in our function call, we used a CPU array, which had memory that was stored on the CPU. Now, the type that we passed in was a vector of float 32s. And in Julia, the vector object is not a bits type because it has references to other locations in memory and doesn't just contain plain data types itself. We can check this by running the isBits type and then passing in the type of C. You can also get the same result by using the isBits function. And since this returns false, this means that when we're compiling this new kernel, this program to run on the GPU, we weren't able to just simply copy this value across to the GPU dynamically and have our code run there. And that's because even if we copied the reference for C, it would be referencing memory on the CPU, which the GPU cannot access anyway. The way that we fix this error is really simple. All we have to do is make sure that the memory that we're trying to compare lives on the same device. So in this case, we can take the C GPU array and copy it back onto the CPU. This is pretty simple because we can just use the array constructor and pass it the GPU array, and this will just copy the memory from the GPU back to the CPU. So now C from GPU will have the type vector float32. And since C and C from GPU both live on the same device, we can use the isApprox function to make sure that the results calculated from the GPU and the results calculated from the CPU were the same. And of course, these arrays are exactly the same. The reason why I use the isApprox function is because we're dealing with floating point arithmetic, but in this simple case, the results are exactly the same. In general, there are many operations that can be directly used on the GPU, just by using Julia's built-in array syntax. And the multiple dispatch system will make sure that the code will run on the GPU instead of the CPU, as long as the types indicate that it's a GPU array. So now let's move over to a different example to see where GPU performance really shines. And so we'll take a look at matrix multiplication, which is an algorithm that underpins many areas of numerical science. And in this case, we want to compare the speed of matrix multiplication using a single CPU core versus using a GPU. To make sure that we're only using a single CPU core for our matrix multiplication, I'm using this line of code which tells the basic linear algebra subsystem, which is BLAS, to only use one thread. Next of all, we'll create two n by n matrices, along with allocating memory for the result of the multiplication of A times B. We'll then benchmark the matrix multiplication function from the linear algebra library on the CPU arrays. But importantly, we're only measuring the time taken for the matrix multiplication and not the time taken to allocate the result C. And so for this size matrix on my CPU, this takes around 111 milliseconds. The way we can move this to the GPU is very easy. We can just change the types of A, B, and C to their GPU counterpart types. And once these types have been created, we can run the exact same function and just change the input types, and this will change the operation from running on the CPU to running on the GPU. But one thing that we have to be careful of is making sure that all of the input types are transferred to the GPU before we start running our operation. When we actually benchmark this function, we get a result of 20 microseconds, which seems quite suspicious. This would indicate that our GPU ran this operation around 6,000 times faster than our CPU, which seems a little bit too good to be true. And in this case, that turns out to be correct, because in fact, we weren't actually benchmarking the time taken for our matrix multiplication operation. We were benchmarking the time taken to launch this operation asynchronously on the GPU. In fact, when we're calling this code, all that happens is we're launching a job to run on the GPU, and the CPU will continue executing to the next line of code, and not wait for the result of the calculation to be completed. In order to time this a little bit more effectively, what we have to do is add in a macro from the CUDA package. If we add in CUDA.at_sync, this will make sure that the following operation has completed executing on the GPU before moving on to execute any more instructions. In this case, this will give us a far more accurate estimate for the time taken to run our code on the GPU. So now for this example, we get a much more realistic benchmark with times ranging from 1 millisecond to 4 milliseconds. If we compare the minimum time for the CPU and the GPU, we'll see that using the GPU here was around 80 times faster than using the CPU. But keep in mind, this was only for the input size where the matrices were large enough. To get an idea of when the GPU is faster than the CPU, I've repeated this experiment across several different matrices sizes, and plotted the results so that we can investigate. Now these results were gathered on the HPC, which has a much more powerful GPU than the one in my laptop. And so the speedups we'll see in this graph are much larger than what you would typically see in a normal desktop PC. Here I've plotted the relative speedup of the GPU, which is in orange, versus the CPU, which is in blue. Across the x-axis is increasing matrix size, so in this case we're testing the matrix multiplication of two n by n matrices. On the y-axis you're seeing the relative speedup from using the GPU as opposed to the CPU. We can see some very interesting trends here, and that is for matrices below the size of around 100 by 100, it's actually much faster to run this operation on the CPU than on the GPU. And this is something you should keep in mind for your own applications. You only really want to use the GPU when you know that you can give it enough work so that it will end up being faster than the CPU. The individual GPU cores are actually much slower than a normal CPU and have a lot higher latency before getting a result, and so for smaller workloads, you expect to see the CPU vastly outperforming the GPU. The story completely changes when you make the workload big enough. For example, if we go up to matrices which are 10,000 by 10,000, you can see an almost 200 times improvement gain by switching to the GPU rather than the CPU. And this graph really is why you should care about GPU programming. If you do operations that can be highly parallelized, for example matrix multiplication, you can see huge performance gains. And if you're doing mostly array-based operations, it's very easy to port your code from running on the CPU and make it run on the GPU instead. Sometimes when we're porting our code to use the GPU, we don't always have our functions written in terms of these array operations. But fortunately in Julia, we can still compile code to run on the GPU even if it isn't explicitly written in array operations. So now let's look at an example of this by looking at a Monte Carlo simulation. So here I have some simple code that runs a Monte Carlo simulation in the form of a random walk. The function that we want to run on the GPU is called random walk, and when you call this function, it will run on the CPU. So let's say we wanted to use this function to run several simulations in parallel. One option we have is to change this code to use array-based operations instead. And for this example, that would be quite easy. But unfortunately, this approach doesn't generalize well to all types of functions, and it can be quite labor intensive, and so we want to avoid that if possible. Instead, what we can do is coerce Julia's type system and the broadcast notation to instead run this code on the GPU. And so what we want to do is write a function that calls our random walk simulation using the array-based broadcast notation. In this case, the broadcast notation makes it so that we're running the random walk function independently for each different element in the array in which we're storing the results. At the moment, we're just using the standard vector type, which is stored on the CPU, and operations that use this type will be run on the CPU. The way that I've written this code makes it very easy to run our operations on the GPU just by changing the type from vector of int32 into a CU array of int32s. So all we're doing is changing the type to a CU array of int32s. And then the rest of the code stays exactly the same. But since we're using broadcast notation, the random walk function will be compiled directly to run on the GPU. So now let's run these two implementations and compare the results. So if you run the first example, the result that we get back is a simple vector of int32s. But if we now call the GPU version of this function, we'll get back an array which is a CU array, and so this exists on the GPU. And then we can call generic array-based functions to process the results. So for example, finding the average position at the end of the random walk. And in this case, these results are similar in magnitude, but they differ. And that's because the simulation deals with random numbers, and the random numbers that are generated on your GPU will be different to the random numbers that are generated on your CPU. But importantly, both of these functions work as expected. We can even run benchmarks for both of these functions, making sure that we use the CUDA.at macro, which ensures that our timing of GPU functions is correct. And comparing these two results, we can see that the GPU was around 5 times faster. And this is a good improvement, especially because we're only changing one type in our algorithm. If we rerun these benchmarks using a much larger value of n, you can see that the speedup is much greater, going from around 113 milliseconds to 814 microseconds. And now this is 140 times speedup. The speedup that we achieved here was actually much better than if we had written our function random walk to use arrays in the first place. And that's because when we were running our GPU function, we were only calling one GPU kernel, which ran our entire function. If we'd have changed this to use array-based operations, instead we'd be running a kernel every time we're inside the inner for loop. And there is some overhead cost to launching all of these kernels. In general, it's better to combine your operations into a single kernel if you can, which can help drastically improve performance. So let's quickly look at the performance difference between these two approaches. On screen we have the fused kernel, which we've seen before, and what's key about this implementation is that we're only using a single kernel. The alternative approach is to use array-based operations in the random walk function itself. In this array-based approach, we're launching several separate kernels for each of the individual array operations, and we're doing this over several iterations in our for loop. If we benchmark these two approaches, we can see very clearly that the fused kernel has much better performance than the non-fused kernel. And for this small example is around 36 times faster for the fused version as opposed to the non-fused version. And hopefully this example demonstrates how useful it is to have a compiler that can take native Julia code and turn it into device code that can run straight on the GPU. And this is one of the reasons why the JuliaGPU ecosystem is so performant while still letting you write quite high-level code. This random walk example shows that you can transfer embarrassingly parallel operations to run on the GPU if the GPU is able to compile the native Julia function that you give it. Later in this video, we'll see some examples of some functions that can't be compiled to run on the GPU. But for now, let's reintroduce the example of our Monte-Carlo Pi estimation to see where we can accelerate an algorithm that doesn't use any array-based operations. So we've covered this code many times during the series, and if you're unfamiliar with this, I suggest you go back and watch one of the previous videos. But as a summary, what we're doing is performing a map reduce operation. And in this operation, we're using many iterations of the throw dart function and combining the results together using the addition operation. Now unfortunately, CUDA does not have an implementation of MapReduce that we can use readily. And that's because the array type that we're passing into MapReduce isn't a CUDA array, and so none of the GPU code will ever get triggered. But let's say we wanted to run the operation on the GPU without writing our own kernels. What we can do is slightly modify the syntax and coerce it into running on the GPU instead. To save some time, I've already implemented this function and I'll just paste it in and we'll explain line by line what it does. On the first line of this function, we create an array to store the result of using the throw dart function. And on the second line, we fill these results using an in-place broadcast notation. In order to make sure that we're calling the throw dart function independently for each of our iterations, I've defined the anonymous function which maps from some input to a value of throw dart. And the value that I'm passing in is just nothing, which is essentially just a null empty type that you can use in Julia. But since we're using the in-place broadcast notation, this function will be called for each element within the darts array. But since this darts array is a CUDA array, this broadcast call will be compiled and run on the GPU. On the next step, we just call the reduce function separately, which adds up the results from everything in our array. And this reduce function works because the implementation exists within CUDA.jl. And implicitly, the result will be copied back from the GPU to the CPU. The final line of this function I've added just for some extra performance benefit. Since we've allocated memory on the GPU, which is a very finite resource, we want to make sure that we free up this allocation once we're finished using it. Since this function won't use the darts array after calling the reduce function, we can tell CUDA that it's okay to free this memory straight away without having to wait for the garbage collector to clean it up. You don't explicitly have to do this in Julia, but it just helps clean up some of your memory if you know you're not going to use it. Just make sure you know what you're doing and you don't try and access the memory allocated by darts after this function call, because you might run into some issues. So now let's benchmark these two functions and see which one is faster. Now unsurprisingly, the GPU version is faster than the CPU version, with the CPU version taking around 2.6 milliseconds in the fastest case, whereas the fastest version on the GPU took around 120 microseconds. This means that this implementation is around 22 times faster, even though the GPU version is doing a lot of extra work by allocating a separate array and calling two kernels instead of a single fused kernel. And not only that, we've also added the extra overhead that it takes to synchronize execution between the CPU and the GPU and transfer any results between them. So the function we've written here is really the start of the performance gains that you can start to see on the GPU. But in the next video, we'll introduce a way in which we can write a custom GPU kernel from scratch without having to use these array-based tricks to try and run our code on the GPU. For now, let's end out this video by talking about some limitations you have when trying to run code on the GPU. Earlier, I mentioned that there are some functions that can't be compiled to run on the GPU directly. And one example of those types of functions are type unstable functions. Now we mentioned type instability earlier in this course, but a type unstable function is one whose types cannot be predicted at compile time. A very simple example of a type unstable function is one where different branches of an if statement return different values. So in this case, one branch will return an integer value and a different branch will return a floating point value. And since the return type is based on a runtime condition, the compiler can't know which of these branches will return when it's compiling the function. We can check that a function has type instabilities by using the @code1 type macro. And if we run this code, we want to check the type annotations for all of our variables. And so for example, x, it's inferred to be a float 64, but the actual body itself returns two different values. And the type instability here is highlighted in yellow because it's a union type. And so the return type can either be a 64-bit floating point number or a 64-bit integer. Sometimes you'll see some function calls annotated with the type any, and this is the worst type of instability that you can have. And in general, type instabilities aren't very good for performance on the CPU and won't even compile for the GPU. Let's confirm this by creating a GPU array and then trying to broadcast this type unstable function to run on the GPU. And the error we get out here is that the broadcast operation that results in a real is not GPU compatible. And the reason why this says it results in a real is because real is a type that can be either a float 64 or an int 64. But real is an abstract type, and on the GPU we have to know exactly what types we're dealing with to be able to compile code for them. And the reason why the GPU has to know the types is because it cannot do any dynamic function calls while it's executing any part of its kernel. And if the GPU doesn't know these types, it can't know which instructions to execute unless it makes dynamic function calls. Fortunately, it's pretty easy to fix this in your own functions. If we go back to our example, we can write a function that is type stable. In this case, we made sure that the return types are of the same type, and they both return float 64s. Now when we run the @code1type macro, we should see everything highlighted in blue instead of yellow or red. And now that we have this type stable function, we can broadcast it easily across all of the elements in our CUDA array, which means this runs directly on the GPU. So finally, let's look at one more example that you will run into very commonly when trying to port your algorithms onto the GPU. So here I've defined this very simple function which just uses scalar indexing. And all this function does is iterate over all of the elements inside an array and try and add up all of these elements into a single variable. So let's say we want to call this function on the array B, where B exists on the GPU. If we call this function, we get an error, and this error is very common to see, so it's important to understand why it's happening. Fortunately, this error gives a lot of information as to why this code doesn't run. And the reason for this is that we're trying to index into the array on the CPU. So this for loop here will run on the CPU, and this operation here indexes an element on that array. And so what we're saying to the CPU is to ask the GPU to find the element at index I, copy that element, and send it all the way back to the CPU. This operation is obviously very expensive and it's very, very slow compared to indexing an array on the CPU. And for this reason, CUDA.jl explicitly bans this operation unless you override it. Because if you're using the GPU, you usually care about fast performance, and this type of operation dramatically decreases the performance of your algorithms. If you read through this error in more detail, it will tell you that you can explicitly allow this type of operation by using allowScalar or @allowScalar. Since this is only really a performance bug, CUDA.jl allows you to overwrite this error behavior, but likely it will just result in much worse performance than if you'd have just used CPU arrays. So let's see just how much performance you lose if you enable this allowScalar option. Calling allowScalar with the value of true enables indexing of GPU arrays globally. So we can run our function again and it works correctly, but the performance won't be very good. If we run our benchmark on the same array but copied to the CPU first, you'll see that this takes only around 350 nanoseconds. We can repeat this benchmark using the GPU array and it will execute much slower. And in this case, it took nearly 10.5 milliseconds to execute. This means it was around 30,000 times slower to use the GPU in this way than to use the CPU directly. And so this is something you really have to be careful of if you're trying to move to use the GPU. Unfortunately, many algorithms are written in terms of scalar indexing, especially within the Julia ecosystem, because these operations are just as fast on the CPU if you use array-based operations as opposed to writing native for loops. And this is one of the most common errors that you'll run into if you're trying to use a random package in the ecosystem using GPU arrays, because those algorithms likely are written in terms of for loops that use scalar indexing. And so you might have to try and find a package that does the same thing but is GPU friendly. But unfortunately, some algorithms can't be easily written in terms of array operations, or if they can be written in terms of array operations, aren't very efficient to write it in that way. If you want to be able to run any algorithm on the GPU or try and get the best performance possible, you'll have to learn how you can write your own custom kernels. We'll cover writing your own GPU kernels in the next video. But for now, let's quickly summarize some of the restrictions that you have with array-based programming methods when you're using CUDA.jl, and some tips that you can use to overcome these restrictions. The first restriction that you'll see is that scalar indexing is disallowed by default because the performance is incredibly poor. In general, you want to try and avoid this programming style when you're using GPU arrays, because running the for loops actually runs on the CPU and requests data to be transferred bit by bit from the GPU. And most of the time in Julia, it's possible to avoid writing for loops directly and just use broadcasting and generic functions instead. Sometimes this isn't always possible, and if it's not possible, you will have to write a custom GPU kernel. The next restriction is that all of the memory required by your computation must exist on the GPU before you run that computation, and the onboard memory of a GPU tends to be much smaller than the host's system RAM. For this reason, I would encourage you to use in-place operations where possible and avoid excessive allocations and copying of memory, because this is a very limited resource. This also has the added benefit of avoiding garbage collection, which can improve the performance of your algorithms. And the final restriction is that broadcasted functions should be type stable in order to be compiled into native GPU code. Luckily in Julia there are a lot of tools for trying to fix type instabilities, and the main tool that you'll use is the @codewarnType macro. This rule also applies when you're writing custom GPU kernels from scratch, and so we'll be covering it a lot more in the next video. Some final tips are to do with generic GPU programming. When you're first writing your code and you're just testing it out and you're trying to get it to run on the CPU, I would encourage you to use functions such as map, reduce, and sum, which can be later easily ported to run on the GPU just by changing the type of the array. This will let you easily test your code on the CPU and be comfortable knowing that it will easily port onto the GPU. If you have quite complicated code that needs complicated indexing operations, you might need to write your own kernel. Fortunately, CUDA.jl allows you to write kernels in pure Julia, which can get compiled to native device code. And there also exist a lot of really good packages like kernelabstractions.jl, which allows you to write these compute kernels in a non-vendor specific way that support a wide range of backends, so you can write a single kernel that can run not only on an NVIDIA GPU, but also an AMD GPU, or perhaps one of the new Apple chips. And this can help you make sure that your code will work on a variety of platforms, so that many people can use your code and benefit from the performance improvements when moving to a GPU. So that's where I'll end this video. Hopefully you feel a bit more comfortable with GPU arrays and you can get started with accelerating your code by using a GPU. In the next video we'll dive into the more advanced topic of writing your own custom GPU kernels.